Okay, lesson 81, we're going to talk some more about complex numbers. Remember that a complex number is a number which has a real part and an imaginary part and is written in standard form as a plus bi, where a and b are real numbers. The set of real numbers is a subset of the complex numbers where b is 0. So if the part that has the I in it goes away because b is 0, then you have a real number, a. The set of imaginary numbers, purely imaginary numbers, is the subset of the complex numbers where a is 0. So if the a part, the real part, goes away, then you're left with just bi, which is a purely imaginary number. So the point here is that the complex numbers contain both the real numbers and just the pure imaginary numbers. The complex numbers have a real part and an imaginary part. Real numbers are when the imaginary part is 0 because b is 0. The pure imaginary numbers are also a subset of the complex numbers whenever the real part of the complex number is 0. So the complex numbers, that's basically the set that includes all the numbers we've talked about in math so far at your time of life. So the complex numbers, we're going to continue to talk about those. An expression like this, which has a complex number divided by another complex number, is not acceptable notation because for a couple of reasons. For one, it is not in the form a plus bi, which all complex numbers have to be written in that standard form with the real part first and the imaginary part second. And second of all, there is a radical in the denominator of this fraction because remember, I is equal to the square root of -1. So right now, this fraction has a square root in the denominator, which we know is not acceptable. So we have to rationalize the denominator and write the complex number in a plus bi form. And the way we do that is just exactly the same way that we deal with any fraction that has a radical in the denominator. We need to rationalize it, get the radical out of the denominator, and in this kind of situation, we will multiply the top and the bottom, the numerator and the denominator of this fraction, by the conjugate of the denominator. So the denominator is for minus 2i, which means its conjugate is for plus 2i. So we're going to multiply the top and the bottom of this fraction by 4 plus 2i. So for the numerator, we're just going to FOIL it. 2 times 4 is 8. And then 2 times 2i is 4i, and then 3i times 4 is 12i, and 3i times 2i is 6i squared. So that's the numerator, and then the denominator. So here we are multiplying conjugates, and that's 4 minus 2i times 4 plus 2i, which means we are going to get a difference of squares. First thing squared minus the second thing squared. All right, so the numerator, we've got 8 plus, and then 6i squared is -6 because I squared is -1. So 6 times I squared is -6. So 8 plus -6 is 2. So that's our real part of the numerator. And then the i's, the 4i plus 12i is 16i. So that's the imaginary part of the numerator. And then in the denominator, we've got 4 squared, which is 16. And then we've got 2i squared, which is 4i squared. So first thing squared minus second thing squared. So in the numerator, we still have 2 plus 16i. In the denominator, we have 16 minus -4, because 4i squared is 4 times -1, which is -4. So 16 minus -4 is 16 plus 4, which is 20. So we have 2 plus 16i over 20, and we know we want to write the real part first, 2 over 20, and the imaginary part second, 16 over 20i. And now we need to reduce the fractions to 1 over 10 plus 4/5 I, and that is the final answer. It has the real part first, imaginary part second. There are no radicals in the denominator. It's just completely simplified and in good notation. Now we're going to simplify another one. So why don't you turn off the video and try simplifying this one yourself, and then you can turn it back on and we can go through it together. Okay, let's run through it. We're going to multiply the top and the bottom of this fraction by the conjugate of the denominator. The denominator is 2i minus 3, so we're going to be multiplying it by 2i plus 3 over 2i plus 3. So for the numerator, when you FOIL that out, you're going to have 4 times 2i here, and you're going to get 8i. And then 4 times 3 is going to give you 12. And then negative 2i times 2i is going to be minus 4i squared. And then 2i times 3 is going to be, well, it's negative 2i times 3. It's going to be negative 6i. And then in the denominator, you're multiplying conjugates. So you're going to have the first thing squared, 2i squared, minus the second thing squared. And so when you do that out, you're going to have 2i on top because you have 8i minus 6i, so that's 2i. And then you've got a 12, and then you have minus 4i squared, which is minus 4 times I squared, which is negative 1. And then on the bottom, you have 4i squared minus 9. And then when you add everything on the top, you've got 2i plus 12 plus 4, so 2i plus 16. And in the denominator, 4 times I squared is negative 4 minus 9. So if we write this in the correct order with the real part first and the imaginary part second, we've got 16 plus 2i all over negative 13, and then we write them completely separately, negative 16 over 13 minus 2 over 13i. And that is the standard form for writing a complex number. Okay, this is another use of the word complex. Lesson 82, we're simplifying complex fractions, and this does not have anything to do with complex numbers. All the numbers we're working with in these problems will be real numbers, but we are going to be simplifying some more fractions that have fractions in them. We call that kind of a fraction a complex fraction. So we have to remember two tools that allow us to deal with these kinds of things. We need to remember that we can always multiply the numerator and the denominator of any fraction by the same non-zero number, and it won't change the value of the expression. So if I have 1/2 and I multiply by x over x, I multiply the top by x, I multiply the bottom by x, I'm going to get x over 2x, which is the same thing as 1/2. It's still 1/2. I didn't change it. It is still 1/2. It's still equal to 1/2. So you can multiply the top and the bottom of any fraction by the same non-zero number, and it won't change the value of the expression. So that's a good thing. We're going to use that. Another thing to remember is that any whole number can be written as a fraction with denominator 1. So if you have 5, you can write it as 5 over 1. If you have 7, you could write it as 7 over 1. If you have x, you can write it as x over 1. So what that is telling you is that whenever you have a whole number, you can just think of it as being the numerator of a fraction whose denominator is 1. So if I multiply 7 over x times x, that x is in the numerator. So that numerator and denominator cancel, and I just have 7. If I write 4 over 10 times 10, that equals 4 because the 10s are going to cancel out because one of them is in the numerator right here and one is in the denominator. And so that's just 4. If I have 2x over y and I multiply that by y, it equals 2x because this y is in the denominator and this y is in the numerator. A whole number is in the numerator. All right. So these facts are going to help us simplify this kind of complex fraction where we have fractions inside of fractions inside of fractions. So when I see a problem like this, where I have a fraction in the denominator of a fraction, what I want to do first is simplify that fraction. That is a complex fraction right there. It's a fraction with fractions in it. It's the smallest complex fraction we have here. It is the smallest fraction that has a fraction in it. So what we're going to do is look at the little fraction that is inside this complex fraction, which is 1 over x, and we are going to multiply the top and the bottom of this whole complex fraction by the denominator of that littlest fraction, which is 1 over x. So the x, that denominator, I'm going to multiply this fraction, a over 1 plus 1 over x, by that. So I'm multiplying the top by x, and I'm multiplying the bottom by x. Just this part. All right, so the a on top stays where it is. The 1 stays where it is. I'm not messing with those yet. I'm just dealing with this one fraction, a over 1 plus 1 over x. I'm going to multiply the numerator of this fraction by x. So I'm going to get a times x, which is ax. And then I'm going to multiply the denominator of this fraction, 1 plus 1 over x, also by x. When I do that, I will distribute the x to the 1. X times 1 is x. And then x times 1 over x is 1, because x is a whole number, and I am multiplying it by a fraction. So that x in the 1 over x is in the denominator. The x that I'm multiplying it by is a whole number, so it's in the numerator, so they cancel, and I end up with 1. All right, so now I have simplified this fraction somewhat. It is still complex, though, because it still has a fraction in it. So the fraction ax over x plus 1 is still a problem. But if I multiply this whole fraction, top and bottom, by x plus 1, that will cancel that x plus 1 out. So I'm going to do just that. So if I multiply x plus 1 by the numerator, I'm going to multiply a times x, and that's going to be ax. I'm going to multiply a times 1, and that's going to be a. So my numerator now is going to be ax plus a. And then in the denominator, I have to multiply everything in that denominator by x plus 1. So I'm going to multiply the 1 by x plus 1, and I'll just get x plus 1. And I'm going to multiply the ax over x plus 1 times x plus 1, which means the x plus 1s are going to cancel. Because if I multiply this fraction, which has a denominator of x plus 1, times x plus 1, which is the denominator of that fraction, then these will cancel, and I'll just end up with ax. So that goes right there. So now I have a simple fraction. This fraction doesn't have any fractions in it. It doesn't have any common factors. You can't factor anything out of the numerator and factor anything out of the denominator. That will cancel. Remember, whenever you have a fraction, you can only cancel factors. There are no common factors in the numerator. I mean, a is a common factor in the numerator, but if I factor it out, there isn't a common factor of a in the denominator that I could cancel it with, so there's no point. So that is how you simplify that kind of fraction. So here's another one. Why don't you turn off the video and try this one on your own, and then you can turn it back on and we will go through this one. Okay, this fraction is in the same form as the one we just did. It has a big fraction with a littler fraction in it, a littler complex fraction right here, which has just a basic fraction in it, 1 over y. So the little basic fraction has a denominator of y, so we're going to multiply this smaller complex fraction by y over y. When I do that, everything's going to stay the same on the top of this fraction. I'm not messing with that yet. The a plus is not being messed with. Now I just need to multiply these two things together. So c times y is cy. And then in the denominator, we're multiplying y times x to get xy. And when we multiply y by 1 over y, we get 1. So that's what we have. Now we have simplified the fraction to where it only has one fraction left in it. And so we're going to multiply the top and the bottom of this whole big fraction by that denominator xy plus 1. And when we do that, we will end up with a simple fraction. So we'll multiply the numerators. B times xy is bxy. B times 1 is b. And then in the denominator, I'm going to multiply a times ax, which is axy. I'm going to multiply a by 1, which is a. And then when I multiply cy over x plus 1 times x plus 1, those are going to cancel. The xy plus 1 and the xy plus 1 are going to cancel, and I'm just going to end up with cy. And so that's it. That fraction is as simple as it can be. There are no common factors. There are no fractions left in it. That fraction is simplified as much as it can possibly be. Okay, lesson 83, we're going to talk about using the rules for exponents in situations where we have variables. Remember the rules for exponents. When we multiply like bases, we add the exponents. So this kind of situation, when you're multiplying like bases, these both have a base of x, and you're multiplying them, you can add the exponents. So x squared times x to the 5th is equal to x to the 2 plus 5, which is x to the 7th. When we raise a power to another power, we multiply the exponents. So if I have x squared and then I raise that to the 5th power, I can multiply those exponents and I will have x to the 2 times 5, which is x to the 10th. So we can use those same rules even when we have a situation where we have variables in our exponents. So here you can see you have an x to the a power and an x to the a over 2 power. So those are like bases. They both have a base of x, and so you can add the exponents. So you're going to have x raised to the a plus a over 2. Then if you look at the other two factors here, you've got y to the 2x and you've got y to the 3x over 4. And those have the same base, y. So you can add the exponents, y to the 2x plus 3x over 4. Now all you can do is get a common denominator. So you can add a plus a over 2. That's going to get a common denominator of 2. So you'll have 2a over 2 plus a over 2. And then for y, the common denominator is going to be 4. So you're going to have 8x over 4 plus 3x over 4. And now if you just add those, you're going to have x to the 3a over 2 and y to the 11x over 4. Okay, here's another one. And this one we have division going on. I'll do this in two different ways. There is another rule for exponents which says that if you divide like bases, you can subtract the exponents. So I'm going to do that way right here. So way 1, I've got x to the a minus 2, and I'm dividing that by x to the a over 2. So those are like bases. They both have an x for their base. So that's going to be x to the a minus 2 minus a over 2. Because again, if you divide like bases, you can subtract the exponents. And then for the y's, I've got y to the a plus 4 divided by y to the 2a. Since those are like bases, they both have y for a base. I can subtract those exponents when I divide those like bases. And so now I just need to, on the left, on the x exponent, I need to get a common denominator for that. So I've got x to the 2a over 2 minus 2 minus a over 2. And then for y, I can just add this up, but it's just a plus minus 2a is negative a. So I've got 4 minus a for that y exponent. And then on the x, I've got 2a over 2 minus a over 2, which is just a over 2. And then that minus 2 is still there. And then I've got y raised to the 4 minus a. So I could do it this way, where I use that rule that says if you divide like bases, you can subtract the exponents. Or I can just bring everything up to the numerator and do it that way. So this will be another way to do it. So I will just bring everything up to the numerator. So I'll have x to the a minus 2, y to the a plus 4, and then I'm going to bring x to the a over 2 up to the numerator and make it x to the negative a over 2. Because if I change the sign on the exponent, I can move that to the numerator. And then for y to the 2a, if I move that up to the numerator, it becomes y to the negative 2a. All right, so now I can add the exponents on my like bases. I've got my x's, so x to the a minus 2 minus a over 2. And then I have y to the a plus 4 plus negative 2a, so minus 2a. And again, I'm just going to I'm going to get a common denominator for this first one. I'll have 2a over 2 minus a over 2, which is just a over 2. And minus 2. And then the y is a minus 2a is negative a. And then you've got plus 4. And on the other side, I wrote it as 4 minus a. So I'll write it as 4 minus a this way. Yeah. So you get the same answer, of course, either way. But just whichever way you think makes sense to you, do it that way. Okay, here's another one. We're raising a power to another power. So we've got x to the a plus 2 raised to the second power. which means that we need to multiply those exponents. So we're multiplying a plus 2 times 2. So we've got x to the 2a plus 4. Why don't you take a try on this one? Turn off the video and see if you can simplify this, and then turn it back on and we'll do it together. Okay, so the first thing we have here is a power raised to another power, which means we multiply the exponents. So x raised to the ab power. And then over here, we also have a power raised to another power. So we need to multiply a times b plus 2. And then in the denominator, we can bring that denominator up to the numerator. In the denominator, we have x to the negative a power. So if we bring that up to the numerator, it becomes x to the positive a power. So now we just have like terms, which we can add the exponents on. So x to the ab times x to the a is just x to the ab plus a. You add the exponents. And then y, if we distribute that a, we have ab plus 2a. And so that would be as simplified as this can get.